space. So for us, thus far, all that I care for at this point is that the state of a quantum system is described by a vector in a complex vector space. As we see later, we can also describe it with a matrix. That vector is normalized. It has a norm that is equal to 1. So that means that the inner product with itself, squared up, is going to be equal to 1. Then we also talked about how quantum systems, whenever they're closed, evolved. And what we know here is that the evolution of a closed quantum system is given by a unitary transformation. That means that given a quantum state, we can obtain its evolved quantum state through the action of a unitary operation. So essentially, going back to linear algebra, this means that I have a vector, I apply a unitary, I do matrix multiplication, I get another vector, and that is just the time-evolved operator. So thus far, we've talked about complex vector spaces, vectors, and unitary operations that map vectors to vectors. This unitary has a special property that it is obtained as a solution to the Schrodinger's equation, which is this equation right here. And we know that the Schrodinger's equation describes the interactions that are in the system, specifically given by the Hamiltonian. The Hamiltonian of the system is nothing more than a Hermitian operator. So again, we've talked about unitary. Now we introduce Hermitian operators. And that Hermitian operator is going to generate the evolution given by my system via this equation right here, which is the solution to Schrodinger's equation when the Hamiltonian is independent of time, which is an assumption that we're going to make throughout the rest of this course. Then the next thing that we talked about was how to extract information out of those quantum states. And we do this through measurements. And more specifically, we talked about what is the probability of obtaining a measurement outcome and what is the state that we obtain post-measurement. So here you can see that what we're doing is that probabilities are obtained by just computing the expectation value of some measurement operators, as we see in this equation right here. And then we can just use this equation to obtain the state of the system post-measurement, right? We know that measurements, if we're working with a complete basis of measurement, then those measurements are going to fulfill this property, which tells me that the summation of the probabilities need to be equal to 1, which means that whenever I run an experiment, I have to get an outcome out of that experiment, right? Finally, we have how to describe composite systems. And here what we have is that we introduce this new operation, which is the tensor product. Again, linear algebra. So thus far, you've seen that most of what we've done is just linear algebra. How do we construct the space that describes a composite system? Well, we have the Hilbert space for each one of its constituents, and we just compute its Hilbert space, with each one with its associated Hilbert space, and we just compute their tensor product. And this is how we're going to build the Hilbert space for the composite system. And the basis of that composite Hilbert space is just the tensor product of the elements of each one of the bases. We saw the example of one qubit, which has just 2 elements in the basis, 0, 1. And whenever we go to 2 qubits, we have 4 elements, right? Just given by the 0, 0 vector, 0, 1, 1, 0, and 1, 1, which is what we usually expect. And then we saw that, this formalism to describe density, quantum systems using a state vector is really nice, but we can also generalize it to describe the state of a quantum system via the density operator. And this is the case whenever we only have partial information about the system, or when our system, we can only have some probabilistic access to it, like this idea that we had of we have a device that doesn't exactly prepare the same quantum state each time that we run an experiment, but it prepares different states with different probabilities. So here we saw that the evolution is given by the conjugation of my density matrix with my unitary U. What I mean by conjugation is precisely this. I take U and I apply it to rho, but I also have to apply U dagger. This is what I'm going to be referring to as conjugation. Measurement probabilities and measurement states, the states post-measurements are given by those 2 equations. And the properties of the density matrix is that the trace is equal to 1, which tells me that probabilities have to add up to 1. And it's a positive semi-definite matrix. And this is telling me that whenever I perform an experiment and I'm going to get an outcome, I'm essentially guaranteed that that outcome is going to be a probability. So essentially, this right here guarantees that the inner products with any vectors are going to be positive. Right. So based on this framework, we're now going to run and try to understand how we can use those rules to understand quantum computing. And we're going to see that this basic set of rules that we have right here is more than enough and associated with some components of linear algebra to understand many quantum computing algorithms, and specifically near-term algorithms. Just for everyone to know, the slides for this course are going to be uploaded to the same GitHub repository where we have the theoretical exercises, the slides, and the coding exercises. So there's already a folder up there that is called lecture notes that contains notes for class 1. So you're free to take notes, but also if you want to get the notes, they're going to be available online. So let's now start to delve deeper into our second class. So first, what I want to do is, we've been talking about the postulates of quantum mechanics, and those have some interpretations to them. And I just want to briefly recall some of them, which are going to come into play in a second. So based on those postulates, we can derive some properties of quantum mechanics. So first, Schrodinger's equation is deterministic. That means that if I know the quantum state that I'm starting with, deterministic. If I know my state at time t, then I evolve it to a time t prime, then I exactly know where my state is going to be via the solution of the Schrodinger equation. But of course, measurement outcomes are probabilistic. And this dichotomy between the probabilistic and the deterministic nature of quantum mechanics is going to play a key role in just a second. Then we also have the superposition principle. Superposition. That tells me that the wave function can be expressed as a linear combination of the eigenvectors of a given observable. And we already know that an observable is a Hermitian operator. And we just repeat this here, Hermitian operator. And that the coefficients in this expansion determine the probabilities of the measurement outcomes. So usually, we've been talking about quantum states that can be expanded in a basis that is of the form, 0, 1, tensor n. And I'm going to be repeating this notation quite a lot. So let me just rephrase what it is here. So we have the old 0 state, and we have the state with the 1, 0, the rest of the 0, and all the way with all the 1s, right? But this is, of course, not the only basis in which we can describe quantum state. This is just, again, if you see what we said here, the coefficients, the state can be expressed as a linear combination of eigenvectors of a given observable. These right here are the eigenvectors of the Z observable. That means the Z operator, right? Because we already know that Z acting on a single qubit state 0 is equal to 0. Z acting on 1 is equal to -1. So these are the eigenvalues of just one particular observable. But in principle, we can think about an observable that has eigenvalues AI and associated eigenvectors AI. And we could always expand our state in this basis, right? So here, usually whenever we use this basis right here, which we call the computational basis, let me use C tilde I. I'm going to denote them as Z, where Z belongs again to the set 0. Sorry, this is like this. 0, 1 to the n, right? So in principle, we can always expand our states in any basis, not just necessarily the computational basis right here. But usually whenever you see textbooks, we sort of prefer the computational basis. And a lot of the work that we do is in the computational basis. Why is this? Well, the fact that we prefer the computational basis is that first, bases are arbitrary. You could always say, I'm going to expand on the basis of X or Y. YZ, it's just a matter of arbitrary choice that we've done. But more than that, something that we discussed yesterday, and we're going to go into more detail today, whenever we measure, we usually have to measure on the basis of some operator. And usually that operator is the Z operator. So whenever you have a quantum state in a quantum computer and you perform measurements, then what you're going to get is just a sequence of zeros and ones. You're going to get a classical bit string with a given probability, right? So if I have 2 qubits and I just measure them, I will get either 0, 0, 0, 1, 1, 0, or 1, 1. And that's why we usually work in the computational basis, because that's the basis associated with the measurement outcomes in a quantum circuit. Whenever you see something that looks like this, without anything else to it, this is sort of assuming that we're going to be measuring in the computational basis of Z. So this is sort of associated by convention. Again, this is completely arbitrary. A measurement in the Z basis. But, keep that in mind that this is just arbitrary. I just wanted to bring this up. So we've talked about Schrodinger's equation being deterministic, measurement outcomes being probabilistic, the superposition principle. Now we can also talk about a very interesting phenomena, interference, which tells me that wave functions can interfere coherently or destructively. This is, of course, as you all know, at the basis of the double slit experiment. And this is also going to play a key role in quantum computing, because a lot of time it's about trying to make the solution to your problem, the wave function, have a coherent and amplify the solution to your problem, where you want all of those states that are not the solution to your problem to interfere destructively, so that whenever you measure, you don't get that outcome. And finally, another property that we just sort of browsed last time is entanglement, which tells us that for many body quantum systems, psi, the state of, let me just actually go back and not write this as an equation. Let me just say the wave function of its constituents only provides partial information about the state of the whole system. So this tells us that, in general, quantum states are not going to be of this form. This is an X. This is a tensor product. Right? Because we have quantum correlations, and our general quantum states are usually going to be expressed as a summation of some coefficients of states that are expressed as a tensor product. So let's be proper here, and this should be a tensor product when J goes to 1 to n, right? So this is what we're essentially going to have in most cases. And just partial information included in reduced states is not going to be enough to describe the whole system. And this, again, will be very important. And for composite systems, and as we said last time, we're just going to consider systems composed of many qubits. We're not going to go to more complicated systems. We're not going to be considering fermionic systems or anything like that. For us, quantum computing is just about a collection of many qubits thrown together, and we're trying to get something useful out of them. And of course, because we're going to be working with a lot of qubits, this means that we need to really, really understand the physics of a single qubit. Because if we understand the physics of a single qubit, we're going to be in very good shape to understand the physics of a collection of many, many qubits, right? So this is just to say we will focus on single qubits and then generalize to n qubit systems. So this is the scope of the work that we're going to be working on, right? So of course, as we know, single qubits, we can think about a qubit as a spin 1/2. We can think about it as as encoding it into a photon. We can encode it into the spin of an electron of the electrons of a nuclei. It doesn't really matter. All that we care for is that a qubit is just a quantum system that only has 2 degrees of freedom. That is, it only has 2 states that it can belong to. And its most general wave function is going to be expressed a linear combination of a state that we're going to call 0 and a state that we're going to call 1. And we know that A0 and A1 are complex numbers. And we know that the absolute value of A0 squared plus the absolute value squared of A1 squared has to be equal to 1 because our state is normalized, right? So let's start to think about linear algebra, because as I said, quantum computing, at least what we're going to be seeing here, is linear algebra. You can just, whenever you're scared about quantum computer, just think about linear algebra, and you're going to see that if you know the basics of linear algebra, you're in pretty good shape for quantum computing, right? So we've already said that this is a 2-dimensional vector space, so we can write this as the elements of the basis of this 2-dimensional vector space, right? By convention, we just assign this as the 1, 0 vector and this as the 0, 1 vector. So that means that with the previous equation, our state psi in vector notation is going to be expressed as A0, A1, right? And you've probably already gotten tired of hearing this many times, but the state of a qubit is usually represented by, can usually be represented in the block sphere. And all the credits for this image go to Wikipedia. Credit where credit is due, right? So we know that in the block sphere, the states of a qubit, they're going to be associated with points in the block sphere. So first thing that you should know about the block sphere. So one, pure states belong to the surface of the block sphere. And from now on, let me just recall that if I define my density matrix as psi psi, for this pure state, we know that our state is pure if the trace of rho squared is equal to 1, or if rho squared is equal to rho, which we can very easily verify in this equation because we have psi, psi, and then we have psi, psi. Know that this is equal to 1, so we have psi, psi, right? So our quantum state is pure because the state is a projector, right? So pure states live on the surface, while mixed states live inside the block sphere. There are going to be points somewhere inside of this sphere. And in particular, we know that, whenever we're talking about having a mixed state, I'll get back to this in just a second. Let me just give you a little bit more context of pure states before we go into mixed states. So, we've described the vector as via two coefficients A0 and A1, but as you can see in this picture on the right, usually we can also define it in terms of angles. What is the angle that my state is tilted with respect to the z-axis? This is what we usually call the theta angle. And what is the tilt with respect to the x-axis? That's going to be the phi angle, right? So in this convention, what we usually define is A0 to be the cosinus theta over 2, and A1 is going to be e to the I phi sinus of theta over 2, right? And again, here you can see that with this equation, we're just, again, determining any point in the sphere is just determined by two coefficients, by two angles, theta and phi. And of course, we know, and we can relate from our postulates of quantum mechanics, that we know that let's think about what is the probability of my qubit being non-zero. The zero state is at the north pole of the Bloch sphere. The one state is at the south pole of the Bloch sphere, right? So if my state is somewhere around here, as you can see in the picture, just like the one that is drawn, we want to see if I measure my qubit, what is the probability that it's going to be on zero? So we want to compute the probability of zero. Using our previous, what we previously learned about the postulates of quantum mechanics, we know that first I need to define a measurement operator for measuring non-zero, for measurement outcome zero. We know that this is going to be a projective measurement, and I can define the measurement operator M0 as just projecting onto the zero state, right? Let's go back to linear algebra. What is the state M0? Well, I have the state right here. I know that from up here, 0 is just the vector 1, 0. And here I have that the bra is going to be simply the transpose vector 1, 0. So whenever I do this multiplication, you can check that I'm going to get a matrix. Again, the outer product of two vectors gives me a matrix that is going to be of this form. So then the probability of obtaining 0 can be obtained as a trace of M0 with my state. And let's start using the density matrix notation rho. If my state is pure, then I'm going to have M0 psi, right? We can go ahead and be a little bit more explicit about this. We know that this is going to be the 0 state with psi, right? And then we can do this very fun trick, and this is a trick that we're going to use quite often, which I'm going to start writing tricks and tips on a different color. Let's use blue, light blue. So trick number 1. Whenever I'm computing the trace of a projector operator, let's call this phi, with an operator O, this is just the expectation value of O over psi. Quick question for the attendants. Is this obvious? Do you know why this is true? If not, I can explain it. If this is obvious to you, I can just run over it. And so I'm going to ask everyone, do you know why this is true? Come on, don't be shy.
Because the operator is Hermitian?
O is generally a Hermitian operator if it's unobservable. But I'm mainly talking about this equality. Why the trace
for the completeness principle?
Exactly. Yeah. That is absolutely true. Exactly. That is absolutely true. This happens because the trace of a matrix A is defined as a summation of the expectation value of A over some complete and orthonormal basis I, where we know that we have something that looks like this, right? So, and this basis is completely arbitrary. We can take the trace with respect to any basis that we have. So in particular, we can choose a basis that contains a state phi, and then, a bunch of states that are orthogonal to phi. This is just a special choice that I made. And whenever I compute the trace of phi O, we use the definition, which is a summation over I of all the elements of this basis I, phi, O, I. And I'm going to choose I belonging to this basis right here. So I'm going to get a term where I is equal to phi. So I'm going to get phi, O, phi. And then I'm going to get a bunch of terms that is going to be a summation of states that by definition we said that they are orthogonal to phi, right? So we're going to get something that looks like this. Phi orthogonal J. Hey, oh, there it is. And this is equal to 0 because we said that our basis is orthonormal. So we only get the first term that survives, and moreover, because it's orthonormal, the normal part tells me that the basis elements are normalized. So this is only equal to phi 0, phi. So this is a trick that we're going to be using quite a lot. That the trace of an operator with a projector is just the expectation value of that operator over the projector, right? And I'm going to leave the proof here in case people want to just check it afterwards. But okay, using this trick right here, we know that this probability is nothing but 0 because this is a projector and this is the operator that we previously had. So this is psi 0, right? And this is nothing else than the modulus of, I kept phi in my hand, squared, right? So now we can see what we previously had for psi. It's just A00 plus A11. So we can just rewrite this as 0. And here we have A00 plus A11. And we have modulus squared. So of course we know that whenever we have 0 with 0, we're going to get a 1. So I'm just going to get here modulus of A0. And whenever I get 0 with 1, I get a 0 because those two states are orthonormal. So this is just what we expect and what we already know. The probability of 0 is just the modulus squared of the coefficient that accompanies the 0. So, you know, this might be obvious, but it's good to do this calculation at least once. And if we use this definition that we have right here, we know that this is going to be equal to the cosinus of theta over 2 squared. Similarly, we can prove that the probability of 1 is equal to the sinus squared of theta over 2. So why do we only have the sinus squared? What happened to phi? Well, we're taking the complex conjugate. So this is just a phase, and the phase is not going to play any role here. So the probabilities of 0 and 1 only care about theta, right? And why is this? So now I want you to start getting intuition about the state of a qubit and measurement outcomes, because this is going to be very important in quantum machine learning, trying to get an intuition of what are the important variables and how our state is going to relate to measurement outcomes. So let's think about it. What are we doing here? We're measuring what is the probability of me being on 0, and what is the probability of me being on 1. And theta is the angle that tilts me over the z axis, right? So you can see that if I have a state with an angle that is smaller than pi over 2, then the cosinus squared is going to be larger, because we're going to get here the cosinus squared of pi over 4. And that means that I'm going to have a larger probability of getting the 0 outcome. And this is, again, because my state, psi, lives in the northern hemisphere of the Bloch sphere. So we can already see how this parameter theta right here is relating to my state lives somewhere in this northern hemisphere. And then I can somehow guarantee that the probability of 0 is going to be larger than the probability of 1, because it has larger overlap with the 0 state than with the 1 state. And then what happens, right? Why doesn't phi play a role? Because you can see that if I have a state psi that is here, let me just put a new copy of the image so that we just don't ruin this one with a lot of information. We know that if I have another state that has the same theta, right, but has a different phi, now phi is going to be somewhere over here, but theta is the same, so it has a phi prime. Those two have the same overlap with the 0 state, independent of what's that phi angle, that rotation that I'm making about the z-axis. both of them live in the same part of the north hemisphere at the same height, and hence they have the same probability of being on zero, right? So this is telling me that, you know, states that live in the top hemisphere have a higher probability of being on zero, and states that live in the bottom hemisphere have a higher probability of being on one. This, you know, very dumb intuition is going to be extremely important. I'm going to write this here. Extremely important for the quantum machine learning implementation. For the hands-on course, for the hands-on exercises. So I want you to keep this intuition in mind, because we're going to use it whenever we're trying to do a classification of quantum states, right? So then let's go to the next thing that we want to do, right? Thus far, we have a quantum state. We can measure it, and we know that we usually measure it in the Z basis, as we said, and we only get probabilities of 0 and 1. So in an experiment, we can prepare an arbitrary quantum state. We perform measurements, and what we get is the state 0 with some probability 0, or the state 1 with some probability 1. And this is essentially what you can do in a quantum computer, right? You prepare states, measure them, and get zeros or ones with given probabilities. But this is not what we want to do, right? We want to do something more interesting. As we've said, as we were talking yesterday, we usually want to compute expectation values, right? You want to compute the expectation value of some Hamiltonian if you're trying to find its ground state. So how do we go about actually finding expectation values? Say that I tell you, I want to find the expectation value of the Z operator, right? I'm going to be using this notation. This is just shorthand for the expectation value of Z over psi. Usually we can also write this here to let people know that this is an expectation value over my state psi. So how do I even compute this, right? Or even if I tell you how do I get the expectation value of the X operator? At the end of the day, I can only measure qubits and have 0 or 1s. So now this is where you start to realize that, you know, for someone that does theory like myself, computing this expectation value right here is just, I take my state A0, A1, I multiply it by this matrix, A0, A1, and I'm going to get a number out of it. But of course, this is not what we want. We're not able to do this in a quantum computer. We have to perform measurements, and we have to compute this out of measurement outcomes. But here, we can actually see that this should be conjugate, right? Did I put conjugate whenever I talked about this here? Yeah, that's fine. So, you know, we can still use this theory to try to get a little bit more intuition about how it is that we're going to get the measurement outcome, how we can get the expectation value of Z from measurement outcomes. For instance, something that we can say is we already know that Z is going to be 1, 0, 0, minus 1. But we've also said in our previous lecture, where we were talking about observables and the principles of quantum mechanics, that given an observable, we can always express it as a summation of its eigenvalues and projectors over its eigenvectors, right? And we already know what the eigenvalues and the eigenvectors of Z are. I believe that we didn't write them anywhere, did we? I thought that we had. Oh yeah, here they are. These are the eigenvalues and the eigenvectors of Z. So we know that Z has an eigenvalue 1 associated with the state 0, 0, and it has an eigenvalue minus 1 associated with the state 1, 1. So we can always express Z as 0, 0, minus 1, 1. And now let's think about what does it mean to compute the expectation value of Z, right? We said that we have to take this inner product, Z psi, and let's just replace this equation right here. What are we going to get? We're going to get psi 0, 0, minus 1, 1 psi. And if we expand, we're going to get psi 0, 0 psi minus psi 1, 1 psi. And this is nothing more and nothing less than 0 psi squared minus 1 sine squared. And we've already said that this is the probability of 0 minus the probability of 1. So we can very easily see from here that by just computing the probabilities, we can actually do stuff that are more interesting. We just have to be smart about how to use those probabilities. For instance, we can compute the expectation value of 0 by measuring a bunch of times, checking what's the probability of 0, checking what's the probability of 1, and then building the expectation value of Z, right? So, in practice, we can go even further, and, those probabilities, we don't know what they are. What we can do in theory is we measure n times, right? And then all that we can do is check how many of those times we get outcome 0 and 0 times we get outcome 1 and 1 times. And of course, we know that n0 plus n1 needs to be equal to n, because again, probability gets conserved. And we can estimate this expectation value as approximately the number of times that we got 0. We're just going to estimate probabilities by their frequencies minus n1 divided by n. So through measurements, we can compute the expectation value of Z, right? And this is going to be crucial because this is going to be at the basis of whenever we're trying to write a quantum algorithm, we want to try to extract information. We want to estimate a cost function. Well, we have to be able to estimate that cost function out of measurement outcomes in a quantum computer, because again, measurement outcomes are probabilistic. So again, this is why being cautious and understanding what's going on is going to be extremely crucial. So now we can actually think about, okay, so how do I compute the expectation value of X? So we can already think about something similar, and we can expand X in its eigenbasis, where we know that X can be expressed in this form, plus, minus, minus, where we know that the plus and the minus state, so I'm just going to write this in this form, is 1 over square root of 2, 0, minus 1, plus, minus 1. These are the eigenvalues of the X operator. The plus has eigenvalue plus 1. The minus has eigenvalue minus 1, right? So how would we go about trying to prepare, trying to measure the expectation value of Z? And let's think about this in a quantum computer, right? Because we said that we can measure, and this is just take your state psi and literally just measure. As we said, measurement outcomes are associated with measuring in the basis of Z. So you can now start to think about, right, so now I want to perform a measurement, but I don't want to perform a measurement in the basis of the Z operator like we've been doing. I want to perform a measurement in the basis of the X operator. So linear algebra, how do we get from one basis to the other? We perform a change of basis. So what I need to do is find a mapping that is going to take me the 0 state to the plus state and the 1 state to the minus state. And there happens to be a change of basis matrix, which I'm just going to write here. And you can actually verify that this is a matrix that takes the 0 state and gives me plus, takes the 1 state and gives me minus. This is pretty easy to check through matrix multiplication, right? This is just 1 over square root of 2, 1, 1, 1 minus 1 times 1, 0. This is just literally this equation. And this is 1 over square root of 2, 1, 1, which is literally the state that we have right here. You can check the other one, right? So what we can do now is just, and this matrix right here is extremely important, and it's called the Hadamard matrix or the Hadamard operator. Why is it so important? Well, it changes basis from Z to X, and that is extremely important. That's something that we can do, right? Of course, there is not just one single matrix that changes of basis. We can think about it here. How do we take states? How do we take a base? What is the change of basis that is going to take me this 0 vector and map it here? And is going to take this vector, right? And then going to map it here. Well, we can also do a change of basis that is a rotation about the y-axis. If I take my block sphere and I do a rotation about the y-axis, let's go back to this rotation about the y-axis on an angle of pi over 2, I'm also going to get another change of basis matrix, right? That is going to give me the appropriate mapping from 0 to plus and from 1 to -1. But for now, what we know is that in a quantum circuit, this is going to look like this. I'm going to send my state through the Hadamard gate, and then I'm going to measure. So we can interpret this circuit in two forms. One, we can think about this as an effective measurement in the x basis, where we just put everything together. Or we can think about, I take my state, I rotate it, and then again I measure in the computational basis of Z. Either one that you prefer to think, whichever one is the interpretation that you rather use, that is going to be fine with me. But in general, and the important thing is to take into account that via changes of bases, what we're going to be able to do now is, and we can write the circuit for this, right? So we have psi, right? And then we send it through the Hadamard. And what it's going to be doing is that it's going to take me to this state right here, plus A1 minus, right? And now we can compute the expectation value of Z by projecting onto the eigenbasis that we need to project onto. Sorry, this should be X. And this is again going to be the expectation value of plus psi squared plus minus psi squared, right? So actually, let me do this differently. Let's think about what this circuit is doing, right? And let's think about this interpretation right here, where we said that we were projecting into a measurement operator M0 that was 0, 0, and a measurement operator 1 that was 1, 1. Whenever we rotate the basis, what we're saying is that we're applying the Hadamard to those operators, and we have to make a conjugation, and that conjugation is H, M0, H, dagger. And you can show that this matrix is Hermitian, so that H dagger equals to H. So this is just H, M0, H. And by definition, this is just plus, plus. And H, M1, H is just minus, minus. So running this circuit does precisely what it's supposed to be doing, and it's computing this expectation value right here. All that we have to do, this should be a minus, sorry. All that we have to do is measure with a change of basis, and we are again going to get 0 and 1 outcomes because that's all that we can get. We just changed our basis, but we at the end of the day get 0 and 1, and this is going to be the number of times we got 0 divided by the number of times we measure, number of times we got 1 divided by the number of times we measured. But now we know that because of the change of basis, that N0 and N1 are associated with the plus and minus eigenvalues of my X operator, right? So you can see that changing of basis is an extremely important tool to be able to compute other expectation values. We can compute the expectation value of X, of Y, or Z. We just need to think about what is a matrix that changes the basis so that now I can measure in the basis that I care for, right? And again, this is going to be extremely important. I'm going to write this as tip number 2. Change of basis prior to measurement allows me to compute expectation values of any Pauli operator. Right? So pretty much we have everything that we need to do, right? We have quantum states. We know how to extract information out of them. Maybe we can ask the question, all right, so let's start to think about a quantum circuit, right? So how does a quantum circuit usually work? So now what I want to do is let's stop focusing for a second on single qubit states. That now we know the basics, and we have those two first tips that are going to be used throughout the course. And I want to make now, I've been promising this for a while, but now it's true. I want to make the transition from pure quantum mechanics to quantum computing, right? So now I want to take that framework that we know, and I want to start thinking about a proper quantum computing system. How can we use the rules that we know to be able to understand how quantum computing systems works? And the way in which I want you to think about all the different tools and tips that I'm going to be giving you is they're going to be sort of like Legos that you're going to be able to use to work, right? So I'm going to be giving you throughout the rest of this lecture small tips like this one right here, or the previous one that we had, which was telling us how to compute some expectation value. And all of those tools are just small things that you have to keep in your mind, and they're going to be useful to building quantum algorithms, to understanding quantum algorithms. So there's going to be a lot of small moving pieces that we're going to repeat once over and over again, and we're going to be using to our end goal of understanding quantum machine learning protocols, right? So that's why I'm going to be marking them in different color and just putting them in boxes so that you can just go back and just refresh your mind with them. So very quickly, let me just refresh the Schrödinger equation. Schrödinger's equation. And we know that in Schrödinger's equation, we have something that looks like this. With respect to t, now I'm setting h bar equals to 1. I have h sine of t, right? And we know that h gives us information about the interactions in the system. So let's start with the physical system where we can build qubits, right? Where we can build a quantum computer. For instance, let's think about superconducting qubits. So superconducting qubits, we need to think about how to implement operations in those qubits, right? Because we need to be able to come up with ways in which we can manage the information that is stored in those quantum systems by making them evolve. And quantum systems, usually, whenever you realize them in some physical experiment, they're bounded by the laws of that physical experiment. For instance, if you talk Loïc's talk and you think about the trapped Rydberg atoms that they work with, those have very different physical laws that are going to govern them compared to superconducting qubits. And those will have Hamiltonians that are different, that tells you how those physical quantum systems interact among themselves and with external fields that you can apply to them. So usually the way that this is going to work is that, we need to think about building my quantum system from interactions, right? So I have from a quantum physical system to quantum interactions, and how to exploit those quantum interactions to perform quantum computing, right? And let's now recall what are the tools that we need to perform quantum computing. And this is in our previous slides from yesterday. We're going to be following the DiVincenzo criteria for performing quantum computing, right? So first, what we're going to need, the first elements for performing quantum computing is one, a scalable physical system with well-characterized qubits. So here we can have superconducting qubits, trapped ions, envy centers, electron spins, optical photons, whatever, right? And as we said, we have one quantum physical system, and those are going to have some physical interactions to them. And we can think about the physical interactions as a set of Hamiltonians that are defined by the physical systems. If I have superconducting qubits, they're going to interact in some way. Maybe we can apply to them microwave pulses or something like that, right? And those pulses are going to define interactions, again, as we said, between qubits and the environment. And the next thing that we have to do with those interactions is think about what are the unitaries that we're going to be able to implement, and what are the states that we're going to be able to implement those unitaries on, right? So the second criteria, and I'm just going to leave some space here because I'm going to write something later, is we need the ability to initialize qubits to a simple initial state, right? So this tells me that I have my physical system and I have some way to prepare a very simple, well-characterized state that I can prepare every single time so that I can repeat my experiments. For instance, if I have electrons that are, for instance, if I have NV centers, I can apply very strong magnetic fields, have all of the electrons point along the direction of the magnetic field, and then I know that this can be, for instance, the old zero state rate, where I have all my qubits pointing in some direction. And then I want to make those qubits evolve. I want to act on them so that I make them evolve. How do I make them evolve? Well, according to the Schrodinger equation, this set of physical interactions is going to define a set of unitary evolutions that is going to be given by turning on the interactions and let my system evolve for a given time, right? So physical system has physical interactions, and if we can control those interactions, and this is why quantum computing is so hard at a technological level, because we need to be able to control those physical interactions, turn them on, turn them off, leave them on for a given amount of time so that we can evolve for a desired t that we want right here, right? We need to be able to control all of that. But if we can control all of that, what I could potentially do is evolve this state to a time psi t by turning on one of those given interactions, for instance, and doing something that looks like this, right? Maybe then I want to do something else to it. So then I can think about, I'm going to turn off this field. I'm going to turn on another one. This is a t of those minus I h k prime. So it's not the same interaction for a time t prime over this state. And of course, we can think about this as a concatenation of turning on and off fields for a given amount of time, right? So the physical interactions are going to be leading to unitary evolutions, which in turn are going to be leading to possible states. And how do I know what are the possible states that I can get in my quantum computer? Well, because in general, the state of this quantum system, I can always express it as the product of a series of Hamiltonians that I have been evolving for a series of times, right? And I apply this to my initial state. So you can think about it as a sequence of pulses that I'm turning on and off and on and off, and just letting my system evolve, right? So the set of possible states is defined by what are the unitary operations, and of course, what is the set of initial states that I can prepare? Because if I can prepare multiple initial states, applying the set of interactions to different states lead me to different outcomes, right? So we can think about this as a trajectory where I start with one state. Yeah, I hear that there might be a question. Does anyone? Oh, I don't know. My mic started doing something weird. Let me just try to quickly fix it. All right, there it is. So what we can think about is making a series of evolution to a sequence of pulses that I'm turning on and off to get to the desired outcome, right? So here we start to see already how quantum computing can be thought from first principles through the interactions of my quantum system. But then let's keep going, right? Because we want to do something else. We also now want to have what is called the universal set of gates. Now, of course, the question is, we already know that we can implement unitaries that are going to be the product of those time-dependent unitaries, where U, T, K is just evolve with Hamiltonian HK for time t, right? And the question is, from a computational perspective, we want to be able to do to fine-tune that interaction, because maybe we want to get to a desired state at the end of the system. So in principle, what we want to try to get here is some sort of set of gates that will give me the freedom to get any possible evolution, which in turn translates to any possible quantum circuit, right? And just very quickly, let me just make the connection between this picture right here and a quantum circuit perspective. What we're going to have is that we can think about our initial state like the old zero, right? And then maybe I turn on a pulse that is going to be making my first qubit evolve, right, for a given amount of time. Then I turn on a qubit that maybe makes this, a pulse that maybe makes these two qubits interact. Then I think about turning on a pulse that makes this qubit interact. And you don't always have to do them in sequence. If you have enough control over your quantum system and you can address your qubits individually, you can always make this in parallel, right? Where I will have something that looks like this. First, I address this qubit with some interaction, then I address this qubit with some interaction, then I address this qubit with some interaction. So this gate-based perspective of quantum computing, you can start to see it already emerge from this perspective of I have quantum systems that evolve through Schrödinger's equation, and I just turn them on and off to do what I want to do, right? But of course, going back to this, we want what is called a universal set of gates. So what does this mean? Usually what we want to do is you want to implement some unitary given by our algorithm. Imagine that you're trying to do a quantum Fourier transform, right? And you're trying to implement, we want to implement the textbook quantum Fourier transform algorithm. Well, this is given by a unitary. Let's call it UQFT. But of course, this unitary, someone came up with this unitary because they wanted a desired outcome, right? So the gates are arranged in this unitary because they know that it maps some input to some desired output. This doesn't mean that I can implement that sequence of unitaries in my quantum computer. What I can do is just, implement unitaries that look like this. So if we have a universal set of gates, what we know is that the norm, for instance, for this QFT matrix and a given sequence of products, unitaries that I'm choosing for a given time and evolving for a given time and choosing appropriate unitaries, I can make this matrix norm essentially as small as I want. I can approximate this unitary by just making a sequence of gates that are allowed by the physical interactions in my device. So essentially, when we talk about universal quantum computing, what we know is that a universal, universal quantum computing means that we can implement any operation. And universal quantum computing can be achieved with a universal set of quantum gates. So that means that I'm going to have a set S of some quantum gates that I can implement, and those are going to be enough so that if I apply a lot of them in sequence and in parallel, I'm going to be able to approximate any unitary, right? And if you want a proper definition about this, from here onward, whenever I'm talking about results such as like this, let's use this right here. There's going to be some theorems that tells us how many gates do we actually need to be able to implement this, right? So let me give you two references, Solo by 2000 and Kitaev 1997. This is Russian mathematics survey 521191. There is a theorem that tells me that a quantum circuit of m constant qubit gates can be approximated to epsilon error. So we say a quantum circuit of m constant qubit gates can be approximated to epsilon error, where error is again the matrix norm difference that we had back there, by a quantum circuit from a universal gate set with, and here you're going to see why we talked yesterday about big O notation, m log m over epsilon gates from a universal set. So this already provides us a way to know that, you know, if I have a quantum system where I want to build a quantum computer that has a given set of physical interactions that forms a physical set, well, that's going to be enough. Out of those very simple interactions allowed by nature, I'm going to be able to implement any unitary. You know, I might have to do more or less depth or whatever, but essentially what this theorem tells us is that if I have a big, you know, textbook unitary, I can always translate this into a sequence of gates allowed by the laws of quantum mechanics in my device, such that the action of those two unitaries is going to be the same. And that's what we want. And this usually has a given depth, right? So now we can just stop thinking about, you know, how do I implement this? There is always a way. Now we can start thinking about building quantum circuits from this set of operators, right? And of course, a question you might ask is, well, what is a set of universal quantum gates? So the most famous set of universal quantum gates is going to be composed of single qubit gates, rotations about the x-axis, rotations about the y-axis, rotations about the z-axis. I have a phase gate. This is a matrix that is 1, 0, 0, e to the I phi, and just a single 2-qubit gate, which is the CNOT. So if you have a physical system that can implement all of those operations, you can essentially do anything in quantum computing. And this is essentially what we want. So we can already think about preparing states, evolving them, and of course, the next thing that we're going to need is we're going to need to extract information out of those quantum states that I'm preparing. So I need a qubit-specific measurement capability. So for instance, and let me just give you the example of superconducting qubits. How do I implement single qubit gates in superconducting qubits? Well, for instance, we know that the energy levels here, I can make transitions between the two qubits, between the two levels of a flux qubit by sending microwave pulses. And those pulses can be through a transmission line that is coupled to the qubit with a frequency that resonates with those levels. So I can implement single qubit gates. How about 2 qubit gates? Well, now I have 2 physical qubits, and those can be coupled by putting an intermediate quantum circuit, which usually could be like a DC squint or whatnot. Then whenever I turn on the interactions or just send a voltage to that intermediate bus, I'm going to have those 2 qubits stuck to each other. And then I want to measure them, right? So in superconducting qubits, what I do is that I couple my qubits to a magnetometer or a microwave resonator, and I can measure in the Z basis, right? So usually what we're going to be able to do is just measure again in the C basis, like we've been saying. So the natural sort of question, the natural sort of things that we can do in a quantum device, and let's use this for our tip number 3, is that the natural sort of initialization evolution, and I did here an extra EV and measurement. And we can now think about, even before the measurement, I do a change of basis, will lead me to compute quantities in my quantum computer that are going to be of this one. They're going to be the trace of, I apply a unitary to an initial state, again, applying a unitary to a density matrices via conjugation, and then I measure the expectation value of some operator O. And this, again, is going to be extremely crucial whenever we're trying to define cost functions for quantum machine learning. They have to be of this one, because this is what naturally we can do in a quantum computer. So this is, again, something that we're going to have to take into account. And of course, finally, we want long relevant decoherence times, because physical systems are not perfect. They are prone to interacting with their environment through some uncontrolled ways. And for instance, in superconducting qubits, this could be because we have a faulty Josephson junction that represents my qubit, right? Or maybe we have imperfections in my chip substrate that is making my qubits not perfectly isolated, and they have some interactions. At the end of the day, this is not something that we want. So, we want to try to keep noise tame, but for the rest of this class, let's just assume that we're going to consider the noiseless case, right? We're not going to get into the details of how noise arises and how noise can be characterized. That's going to be probably for Thursday or Friday. But for now, let's assume that we're not going to have noise. And for instance, and just now that I reminded myself, superconducting qubits, they are even extremely sensitive to cosmic rays. So you're using IBM's quantum computer. There's cosmic rays coming through Earth every single day. Well, those cosmic rays can cause some of those bits to flip. So, there's a bunch of sources of errors that we have to worry about. But for now, let's just worry about this thing right here, which is just initialize my system, send it through a quantum circuit, perform measurements, right? So this is essentially all that we're going to be caring for. So
I'm sorry for interrupt you, but I have a question.
Sure, perfect.
Just to be completely sure, we can just say that the initial state of our density matrix is established by pure states, right? I think that was one of the exercises that we did yesterday, but we can guarantee that the evolution of these pure states will remain to be pure.
Correct. So if you have a faulty system where you don't have, for instance, if during the evolution you're not exactly turning on and off the interactions that you want because you don't have that level of control over your quantum system, like we assume that we have here, then yeah, you're gonna have a mixed state at the end. But for now, we're gonna assume that all of our operations are perfect. I can exactly turn on the interactions that I want for the duration of time that I want, so that my circuit is going to be unitary, so that the evolution is going to be unitary. If not, what you can think about is, as you said, I prepare an initial state that is pure in the best case, and then I send it through a quantum channel, right? And then I perform measurements. So instead of having a unitary evolution, you can think about the evolution given by some quantum channel where you take into account the errors that you have in the imperfection in your control system, and the errors of your qubits interacting with the environment. This is, of course, more realistic, but of course, more advanced model of quantum computing. For the purposes of what we want, we're going to assume this. But if you wanted to do quantum computation with this model, all that you have to do is here put the action of the channel over your quantum state, and then you measure some operator. Of course, there is the unitary channel that is just apply U rho U dagger. So this picture here is, of course, more general, more realistic, but for now, we're just going to consider unitary evolutions. But you are right. In general, you cannot guarantee that your state is going to be pure at the end.
Oh no, I mean, I just wanted to verify if we were just guaranteed that we were working with pure states through all the time.
Yes.
Thank you.
So, and then, okay, let me clarify this. Yes, so we're going to assume that this is just going to be a pure state. So, yes. And that.
Excuse me, Marco. Sorry, I want to add something to the question.
Yes.
Okay. So as long as I understand, if I have a pure density matrix with a pure state, it should remain in pure state, right? So, but when we have that is not a pure state, you change to mixed states and some elements of current, that is given by the change of basis, or that is given by what?
So, okay, so a change of basis is a unitary matrix. And as you said, unitary matrices leave me in pure states. And just very quickly, as an exercise, let's check that. Let me just make this here a mathematical space. Assume that you have a pure state psi 0, and I'm going to apply a unitary to it. And we can, in 2 lines, check that a unitary, like a change of basis, does not change my purity. We said that a state is pure if rho squared equals rho. So we can actually check right here, psi 0, u. Then I apply, again, the same state because I'm computing rho squared, psi 0, u dagger. Sorry, this is u dagger u. And here's a dagger. So this is the evolved state. This is the evolved state again. So I'm computing rho squared. U dagger is equal to the identity. So I get u psi 0, psi 0, psi 0, psi 0, u dagger. This is equal to 1. So I get u psi 0, psi 0, u dagger. So unitary operations and changes of basis preserve the purity of my quantum system. So if I start in a pure state, I have to end up in a pure state. So a change of basis cannot change the purity of my system, just like a unitary operation cannot change the purity of my quantum system.
Okay, thank you.
Yeah, thank you for that.
So we have unitary operations. Let me just try to put this here with more space so that when people read this, they know what this is: preserve purity. So that, again, yes, as you said, changes of basis, unitary operations do not preserve purity. So that means that if I have this circuit model and I start with a pure state, I'm going to end up with a pure state at the end. This is absolutely correct. So one final comment in this, I'm just cheating a little bit. I'm just saying that we're going to compute the expectation value of some Hermitian operator O. So what can that Hermitian operator O be, right? So I'm going to add an addendum here, which is going to be tip number 3.2. I don't know. This is going to be 3.1, which is going to be the operator that we're going to be measuring. We need to be able to efficiently compute its expectation value, right? And we've already seen that even if we only measure in the basis of Z, we can always compute the expectation value of other Pauli operators by performing a change of basis. So given this, what we're going to assume is that this operator O is usually expressed as a linear combination of some coefficients. I'm always using C, so I should stop doing that. Let's use like di of sigma mu on qubit 1 times sigma mu on qubit n, or sigma mu k is just x, y, or z. So what we're going to assume is that we are going to be computing either the expectation values of things that look like Paulis, tensor products of Paulis. For instance, I'm going to compute the expectation value of z, or I'm going to compute the expectation value of xx, or maybe x, y, z on qubit 1, on qubit 2, 3, on qubit 1, 4, 5, whatever. But this is the sort of things that I'm going to be computing. Or the second alternative, I'm going to be computing operators O that are going to be expressed as a summation of EI and projectors onto bit strings. Because this is very simple to compute. Imagine that I tell you O is just the projector onto the O0 state, right? Then how is this going to look like? The trace of U, rho 0, U dagger 0, 0. I'm going to write this as a vector. So I'm just going to define 0 vector is equal to the O0 state. Well, again, we can use tip number 1. This is just equal to this thing right here. And we know that this is just the probability of 0. So if we can, and this is something that we can do, right? We just measure a bunch of times. We check how many times we got 0, and we can estimate this through a frequency. So these two are going to be the sort of operators that we can measure and we can efficiently compute in our cost function, provided that the summation has a polynomial number of terms. If this summation has an exponential number of terms, and we have to measure an exponential number of times to estimate all of those terms in the summation, my algorithm is not going to be efficient. It's not going to be better than any classical algorithm, and then I'm done. So we have to assume that O is expanded into poly n terms. And then this is a cost function that I can compute efficiently by just measuring probabilities of bit strings or making some change of basis, doing some classical post-processing to my expectation values, to my probability outcomes, and measuring the expectation value of polys, right? So this is the sort of operators that we're going to be using. And this is going to be extremely crucial because the next thing that we're going to do, and this might actually be a good early stopping point, we're going to be talking about how to use now the basic sorts, rules that we know we can implement in a quantum computer to actually build quantum algorithms. So the next thing that we're going to be talking about is how to build a variational quantum algorithm. And later on, and a quantum machine learning model. So here, let me just define acronyms because we're going to be using them quite a lot. QML for quantum machine learning and VQA. So just so that I give you an idea and a little bit of spoiler of what we're going to be doing in the remaining of our class after our small coffee break, is going to be, we're going to be using DiVincenzo criteria and what we know we can do in a quantum computer, which is prepare states, evolve them, and measure, to try to now build something useful out of a quantum computer. How can we actually solve problems of interest with this basic sort of rules? So for you to understand the progression, we first built the basic rules of quantum mechanics. With those basic rules of quantum mechanics, we thought about how to generalize them to implement quantum algorithms or how to implement quantum computations, right? We essentially just use Schrödinger's equation and how to measure qubits, right? And now that we have expanded the basic tools of quantum mechanics to quantum computing, we're going to see how we can actually use that to solve practical tasks of interest. So I think that this is a good stopping point. We will reconvene here at 11:10 my time, 12:10 your time. So that gives you 17 minutes to have a coffee, get some water, and I'll see everyone. So if you want to get us on our coffee break, that should be very useful. All right, everyone. I hope that was an enjoyable coffee break. Got me some like a ridiculously large cup of coffee to get through the morning. But I think we're ready to continue with our class. Now we're going to be delving a little bit deeper into the specifics about how to actually build and what are the ingredients that are needed to build a variational quantum algorithm or quantum machine learning model from the aforementioned steps and ingredients that we had right here. So just very briefly, public service announcements for people that are enrolled in the course. Please remember that today, at the end of this second lecture, we're going to be taking the official screenshots like photo for the event. So please stay tuned. Don't leave the call after the class ends and after we stop broadcasting, because we're going to be taking our screenshots. All right. That being said, we have the basic rules for quantum computing. We know how to build unitaries, how to initialize states, how to evolve them, and how to measure them. So now the goal of variational quantum algorithms and quantum machine learning, as we've been saying, is to make practical use of near-term quantum computers. This is the sole and ultimate goal, near-term, of variational quantum algorithms and quantum computers. How can we get the best out of those limited, qubit limited and error-prone devices? And as we said here, there are multiple, let's start with variational quantum algorithms, more general. Let me put this image here. There are multiple things for which multiple applications for which variational algorithms have been envisioned for. So, as you can see here, there are some mathematical applications. They've been envisioned, for instance, finding ground states. Is my microphone off? Okay, so Stephanie, I think that it might be your audio setup that is not working. But thank you very much for pointing it out. I had like a mini heart attack thinking that I've been talking for 3 minutes just by myself. So please let me know. I'm going to wait a little bit for you to try to figure this out. If someone can type, might. So let's hope that Stephanie is able to figure this issue out. I'm just going to give her a little bit longer. All right. Felipe, maybe you can guide her in chat and try to see if you can help her. I see that she just left the call. Hopefully she will be able to rejoin and get the audio back. So as we were saying, Stephanie, I see that you've rejoined. Please let us know in the chat if the audio is working for you now. Okay, so there are many applications for which variational quantum algorithms and quantum machine learning models have been envisioned for. And out of this, we're going to actually see how you can implement some of this. So here, of course, what we know and what we've been discussing is that variational quantum algorithms and quantum machine learning models are, at the end of the day, hybrid methods. So what this means is that usually they're going to follow the scheme that is presented right here. So what does this mean? So in a hybrid model, the first thing that we're going to be wanting to do is we have a given problem, given a problem of interest. And again, you can think about a problem of interest as anything from this picture right here. The first thing that we want to do is we want to encode this problem into an optimization task. This usually means that we're going to define a cost function. Define a cost function, which we're going to call from here onwards C of theta vector, where theta is going to be a set of trainable parameters. For now, let's just assume that we don't know what they are. They're just a set of trainable parameters. And there's certain properties that our cost function needs to fulfill. for instance, what do we want from this cost function in order for it to be a good cost function? Because in principle, for a given problem, there is not just one cost function. There's a lot of them that one could potentially define. So how do we know that the one that we choose is going to be a good cost function and is going to be useful, and we're going to be able to use it to train and get the solution of the problem that we want? So the first thing that we want for a cost function is for it to be faithful. So what does faithful mean? Faithful means that there exists an optimal set of parameters, C of theta, where theta star is defined, and I'm going to use this notation, argmin over theta of C of theta. This just means this is the set of parameters that minimizes my cost function such that, for instance, the cost function is equal to 0. And this is the absolute minimum of the problem, right? So in this case, we know that there exists a set of parameters that leads me to my cost function being 0, and this means that I solved my problem. So in this case, we're going to be thinking about we're trying to reach the global minima of the function. In principle, you could be trying to reach the global maxima, but for convenience and because this is what people usually think of whenever you do like gradient descent, you're trying to go down. So we're just going to stick to that convention and say that we want to minimize our cost function, right? So we want our cost function to be faithful. That means that there exists a solution, right? We can actually find the solution. We also want it to be operationally meaningful. So what does this mean? We mean that small cost function values have a meaning. So if I have C of theta 1 smaller than C of theta 2, that means that the set of parameters in theta 1 are closer to the solution and are giving me, even if I stop here, even if C of theta 1 is not the optimal solution, maybe it's a good enough solution. So it's closer to the solution and has better quality solution and better quality. So that we know that we can actually compare results by just how close they are. I don't want a cost function that just, if it's 0, I know that the state that I'm preparing or the set of parameters is good. Maybe I didn't get to exact 0. Maybe I got to 0.001. Is that useful? It should be. Maybe if my cost function is a good cost function, that should be a good solution. It's close enough, right? So it should be operational and meaningful. Then we want things that maybe if we're trying to aim for a quantum advantage, ideally, this is a cost function that cannot be efficiently estimated on a classical computer. Because if it can be efficiently estimated on a classical computer, then it's not obvious where the quantum advantage is coming from. But if my cost function cannot be classically estimated on a quantum computer, then we just need to guarantee that the computational complexity is not exponential, and we're good to go. And that leads us to the next one. It has to be efficiently computable, efficiently estimated on a quantum computer. I want to make a cost function that, estimating it's not going to require an exponential number of resources, because if it does, then we're screwed. So this, usually means computational complexity. And if we're aiming for quantum advantage, that is maybe in order poly n, which means that it scales polynomially with the number of qubits and not in order, for instance, e to the n, because this is exponential and this is the scaling that we expect from classical algorithms. So if we have an algorithm that is exponential, this is we usually don't use basis e, we usually use basis 2. So I'm just going to write this 2 to the n, because that's the dimension of the Hilbert space. So we don't want this. So we do not want this. And then, we want it to be trainable. That means that we need to be able to guarantee that we can train the parameters, that we can just be standing on one point of the cost function landscape and find an optimization direction that takes me to another cost function value of smaller, another point with smaller cost function value, right? And then if we're dealing with noise, maybe we want it to be noise resilient, so that noise will not be such an issue when analyzing the cost function, because maybe if it's too sensitive to the effect of noise, and too much noise will make it so that I cannot use it, then I'm in a very big problem. So to run people through this series of steps that we're going to be giving for a quantum algorithm, and this is going to be related to the first exercise in the Python code, let's give an example. So my example is very simple. Given a 1-qubit system that is initialized in a state psi 0, it could be the 0 state if you want. You know, maybe it doesn't necessarily have to be. We want to train. We want to, let's not say train. We want to prepare the goal. This is a problem, is to prepare the ground state of the Z operator. Right? So this, you might be familiar with this if you've already done the first exercises in the Python code. So what cost function can we define here? So we've already said that our cost function have to be of the form trace of U. Let's go back to this pure state notation, because let's avoid confusion. U dagger O. So who is O going to be? Well, in this case, it's very simple. We can just make it such that trace of U psi 0, U dagger H. And this is going to be a lot of times whenever we're trying to find the ground states of a Hamiltonian. This is going to be another tip. I believe this is tip number 4. Many VQAs encode the optimization problem onto the task of finding the ground state of a given Hermitian operator or Hamiltonian, of a given Hamiltonian H. In this case, the problem is already in this form, so we don't have to worry. And let's think about this. How do we know that this is actually going to be a good way of estimating the cost function? So in this case, my cost function C of theta is going to be, I initialize my state in the 0 state, right? So I have something that looks like this. And then I'm going to send it through a parametrized quantum circuit. We're going to get into a little bit more details about this in just a second, so don't worry too much if you don't know what U of theta is. We're going to explicitly delve deeper into this in just a second, right? So we're going to apply U of theta to this state. So we're going to conjugate. And then we're going to try to estimate the ground state of this Hamiltonian, right? So we're going to perform measurements. And via those measurements, we're going to try to build C of theta. How do we know that this cost function is faithful? Let's try to verify that the previous steps that we were requiring for a good cost function are actually good for the case whenever we're trying to encode the problem into finding the ground state of a given Hamiltonian. So first, let's check if it's faithful. How do we know that this cost function is faithful? So we know that C of theta is going to be the trace U theta psi naught U dagger theta H. Let me do two things now. First, we know that any Hermitian operator, any observable, we've already said this, can be expressed in its eigenbasis. So let me define E as the energy levels of this Hermitian operator, Hamiltonian, and these are the eigenvectors, right? Second, for simplicity, let me define psi of theta as I apply U of theta to my initial state, psi 0. Is this blue color all right? Can you actually see it? I think I'm using the wrong shade of blue color. I should be using the clearer one. I hope up to this point it's not too bad. I'm going to change from now onwards. So what is the cost function given this, right? We can now replace this by the trace of psi theta. So there is psi theta. And we have here, I replace my Hamiltonian summation of EI, the projector onto the eigenvectors. We can take the summation out because of the linearity of the trace. Okay, thank you very much, Rodrigo. I think, let me know if this is better. I think this lighter shade of blue should be better. Yeah, I realized later that I was using the wrong color. This is a trace of psi theta, and here we have projector into EI. We use tip number 1. What's the expectation value of a projector? It's nothing else but this. We've already done this multiple times, so this should come at no surprise at this point, right? So the cost function value, essentially, it's telling me it's a weighted sum of the different eigenvalues of my Hamiltonian, each one of them given by my probability of the state being on that state. So this is a weighted sum of eigenvalues of H by the probability of the states let me see if I can get this working. Perfect. Of the state psi of theta collapsing to the associated level, energy level. I'm trying not to go to the next page because whenever this is going to be a PDF, it's going to be a pain trying to understand what's going on with text split over 2 different pages. So that's why I'm trying to put everything here. I think that's going to be better. All right. So what does this tell us now? If you look at this equation, all of those quantities right here, they are greater or equal than 0 because they are probabilities, right? So they're numbers between 0 and 1. So when is this cost function minimized? We can think about this now as I have my states. Let's go back here, psi of theta. And this has a given probability of being in the ground state, E0. It has a given probability of being in the first excited state, and so forth until we get to the last excited state, which is ED minus 1. Because I started on 0, I only have D, right? Instead of, I mean, I have D in total, but I started in 0. So this state has probability of being in all of those energy levels of H. And this...
Sorry, Martin, can you hear me?
Yes.
Okay, just a question. Okay, that probability is just a probability, or is the eigenvalue?
No, it's the probability. Because okay, the probability, okay, let me give it here, is the probability that I'm in the ground state is given by this overlap. And let me just change the order to keep the convention that we've been using right here. So I have, this is the probability, and this is the energy level. So I have a given probability that my state is in each one of those energy levels.
Okay, thank you.
Right? And this summation is going to be minimized whenever my state is always in the ground state. So I know that E0, here, there it is always a lower bound to C of theta. And it's minimized, so this equality, this with equality, so this is an inequality, and the equality holds. So that means C of theta equals E0 when my state, psi of theta, is always in the ground state. So it's in the state E0. So this is a faithful cost function. It's minimized, and its minimum value is E0 whenever my state is in the ground state of this Hamiltonian, right? So that's good. So is it operationally meaningful? Imagine that now I have psi theta being A0, E0 plus A1, E1. Well, this is going to have a smaller expectation value than a state psi of theta prime that has some component in the eigenvalue, in the ground state, and some component in the highest excited state. So here C of theta is smaller than C of theta prime, because this state is closer. It lives in this region. Now I can use this right here, right? There's a high probability that whenever I measure, it's going to be in one of those two states. So I'm very close to the ground state. So it's also operationally meaningful. So this is a good cost function. And this is a cost function that we're going to use for a lot of our implementations. We're going to try to map the problem into trying to find the ground state of a given Hamiltonian. I'm not going to even bother putting this into a big box because it's just going to be too much. I'm just going to make it like this, so that we know that this is a quite large, very important tip number 4. So the next thing that we need to do is, we've already defined this problem right here of trying to find the expectation value of Z. So here we know that we can just define my cost function as C of theta is going to be the trace of U. Let's actually just reuse what we had right here and just replace this by Z. So this is our cost function, just going to be the expectation value of Z, right? So how do we estimate this cost function on a quantum computer? In this case, we're not going to worry about this not being estimated on a classical computer. It's a toy model. It's 1 qubit. So, you probably can estimate this in a classical computer. But all that we care for is that we need to be able to estimate it in a quantum computer. So how do we estimate this cost function in a quantum computer? We measure n times, see how many times we got 0, see how many times we got 1. So this is a cost function that, using what we previously discussed about single qubits, we know how to compute. We know that we just need to compute those frequencies, and we are good to go, right? So then the next question that we need to ask is, all right, how do we keep going from here? What's the next thing that we need to do for a variational algorithm? The first thing that we said, and it's been a while since we've been here, so I'm going to go back, is we need to encode the problem into an optimization task and define a cost function. The second thing that we're going to have to do is we're going to define an ansatz. And this is a word that you're going to use quite a lot, that you're going to read a lot in the literature. Amira used this word, which is U of theta. So ansatz, just to give you the proper meaning, ansatz is an assumption about the form. So in our special case, defining an ansatz means telling, or well, let's use defining or setting what are the gates in U of theta and how they are placed. So we need to literally say who U of theta is. So this is why I said, when previously I was saying we need to be able to say who U of theta is. Well, this is the next step. So all that we know is that we're going to have something that looks like this, U of theta. And this is what we call, again, and this might already be redundant at this point, parametrized quantum circuit. Right? Usually what we're going to be doing, and we're going to see that this is in general case specific, which is a form of the parameterized quantum circuit, is going to depend on the implementation that we're going to have in hand. In just a second, whenever we see a couple of specific implementations, I'm going to specifically give you what is the appropriate choice for that. But in general, all that we're going to say is that essentially every parameterized gate, any parameterized unitary, we can always express it in this form. It's going to be a product when L goes 1 to n of E of minus I, theta L, H, L, how should I call this? Let's be like this for general. So we're always going to have a product. That means that it's just going to be a sequence of unparameterized quantum gates, like CNUTs that have no parameters, and parameterized quantum gates. So this is a mathematical equation that all that it's telling me is, in words, U of theta, and I'm going to try to use vector. I should be using vector everywhere, so sorry if I forget, is built out of parameterized and unparameterized gates. You know, that doesn't tell you a lot. I know. We're going to get to this in a second. So let's go back to our example. We had this example finding the ground state of Z, right? And we know that we start with the old zero state. So how do we go about trying to find the ground state of the Z operator? Well, it's a very simple question. We know that it's just the one state. We just have to get our zero state down to the bottom. So a way to do this is we just take our zero state, and for instance, we do a rotation the y-axis on an angle theta, right? And essentially, all that this is doing is, I don't have to draw this. This is why I got this, because I'm very bad at drawing. All that this is doing is taking my z state, my zero state that is up here, and I'm going to be rotating around the y-axis. So remember, it's a rotation about here on an angle theta. So I'm going to get to a state here by an angle theta, right? And of course, this is a problem that we can solve. We don't even need to build a variational algorithm for it, but let's do it, because it's going to be a good example of just learning how the different steps works. So that's the second thing. We need to create an ansatz for my unitary. Then 3, I need to design a circuit that allows me to measure the cost function. And this is going to be important because there is not one single way of defining the cost, of measuring the cost function. And we're going to see that there's actually multiple ways to do this. So in our previous example, whenever we had finding the ground state of Z, we have this. We make an RY rotation of an angle theta, and then we're going to measure in the computational basis, because we already know that C of theta is going to be N0 divided by N minus N1 divided by N, right? And that's something that we can do. The one thing that we have to be careful here is that how many measurements do we need to use, right? So imagine that I give you a coin, and you know that it's a biased coin, and you need to find the probability of tails and the probability of heads. How many times are you going to flip it? Of course, if I just flip it once and I get heads, that doesn't mean that the coin always lands on heads, right? That's not true. I just did too few coin flips. If I do 1,000,000 shots, I'm probably going to get a very good approximation of those probabilities. So here, what you have to be careful is that whenever you estimate a quantity through measurements, those measurements, for instance, if I estimate the probability of 0, like N0 divided by N, I'm going to have an uncertainty, a statistical uncertainty that's going to be of the order 1 over square root of N. So this right here is my statistical uncertainty of estimating the probability of 0 due to finite sampling. So this is going to be extremely important. So this is going to be something to keep into account. Tip number 5. Remember again that the only way that we can extract information out of a quantum computer is through measurements. Remember that the precision error due to finite measurements is 1 over square root of N, where N is the number of measurement shots. So this is a word that we use quite a lot in the community. shots, which tells me how many times I'm running my quantum circuit and trying to estimate quantities, right? So then fourth and fifth, we need to determine a parameter initialization strategy. So, you know, I have a quantum circuit that has some parameters. What are those set of parameters going to be initially? Well, you know, maybe there's a good way to know that, maybe not. A lot of times we're just gonna randomly select those parameters and just start my optimization from there. And because we're talking about an optimization, we need to pick up an optimization method. What is the method that I'm going to be using in this hybrid model that we have right here to train the parameters? So let's look at what we've had right here. So let's try to break down this picture. We have a cost function. We've already seen different ways in which we can define it. We know that we have to define an ansatz. Then with that ansatz, we're going to send our state through a quantum circuit, and we're going to perform some measurements. Those measurements, we might be able to do some classical post-processing to estimate the cost function, like probability of 0 minus probability of 1, right? That we have to do it on a classical computer. My quantum computer is not doing that automatically. So this is what we do in a classical computer. We get our cost function value, and we can now think about navigating the cost function landscape. And now we use a classical optimizer to do this. So we can actually go one step further with this very simple example. And if we assume that we start on 0, we know that the cost function value as a function of theta is going to lead us to a landscape that sort of looks like this. Where here, evidently, I have pi over 2. So essentially what we do is whenever we randomly initialize, we're going to pick a set of parameters right here. And the goal is to pick an optimizer that is going to be giving us new sets of parameters and each step that is going to somehow take us closer to the minima, right? And after a sequence of steps, it's going to converge to the actual value that we want. So this extremely simplified example of finding the ground state of Z, this is essentially everything that people do whenever they're working with variational quantum algorithms. You know, it just has extra steps, but this is essentially it. So if you understand and you follow this example of finding the ground state of Z, you're good to go for the rest of the example. They just have some more or less steps, right? So up to this point, before we get into one particular example, are there any questions?
Yes. Can you hear me, right? Yeah, sometimes I have problems with the internet. But okay, the question is that you said that we can pick up an optimization method, but do you have any recommendation for us?
Good question. That's a great question. So people, when variational quantum algorithms were starting, people were using classical optimization methods, right? So people have been working in optimizing classical cost functions for machine learning and whatever for quite a while. So there's a lot of optimization methods. Optimization methods are usually split into two: gradient-based and gradient-free. Gradient-based use information about the gradients of your cost function, and they usually have better convergence rates because you're using more information. You actually know the direction that leads you to the steepest descent. But it has the problem that you need to be able to compute the gradient, right? And it's not obvious that you can always compute the gradient. As we will see later, for variational quantum algorithms and for cost functions that are of this form, right here, you can always compute the gradient analytically using a quantum circuit. So that's going to be, it's one of the key features of variational quantum algorithms. A gradient-free, they always work. Gradient-free are going to be in Python in the code that you have. We're just using a black box optimizer from the SciPy optimization kit, and we're using Cobila. Why do we use Cobila? We've heuristically shown that it works well in the absence of noise. You can also use like the Powell method. You can use SPSA for batch optimization methods. there is no one easy solution. What has been shown is that some of the optimizers that people have developed for classical methods, whenever you put them in a quantum setting in the presence of noise, they underperform. They don't perform too well. And the other thing is that those optimizers, they don't take into account that, we have shot noise. They assume that you have machine precision because that's what they're built for, right? In a classical computer, you always have machine precision, even double machine precision, right? So 30 digits of your cost function or whatever. In a quantum computer, we don't have that. So a lot of times people have been developing what are called quantum-aware optimizers, which are more advanced optimizers that take into account some of the limitations, like the presence of quantum noise, the fact that you have to do finite sampling. Those are more advanced. You can read about them. For now, what I would say is, for small-scale implementations, essentially whatever classical optimization method that you like is going to work. If you want to do gradient-based, then you have to know how to compute gradients. That's one of the exercises in the theoretical guide 3. So we're going to get there eventually of how to actually compute gradients. But, this is heuristics, just like classical machine learning. What's the best optimizer that you use to train a classical machine learning? Everyone has their favorite that they've learned how to fine-tune, and that's the one that they use. So this is extremely similar. For now, the one that I would recommend is Cobila. It has fairly good performance.
Okay. Just one more question. Maybe if another person wants to make a question, let's do it.
Go ahead. We have time. I can take other questions afterwards.
Okay. This is related to the optimization methods. I was trying a time ago the Bayes-Hopping method. That is, they step in a random fashion, but they make a local search for the minimum. But they use several methods like Entanglement and other methods. The question is, do you think that that is a good approach using the Bayes-Hopping method, or do you have any recommendation?
So I've seen people use Nelder-Mead and simplex-based methods. Those are gradient-free, and they work pretty well. Again, if they are going to perform better, I guess it's going to depend on the task at hand. Quantum landscapes can be very particular. They have some difference with classical landscapes. People have even thought about non-local searches, like global searches. And, again, here what I would say is it's a lot of trial and error. Just yesterday, there was a paper that was comparing 4 different methods, Cobila, SPSA, and whatnot, just on one specific problem and trying to see which one performs best. So this is open area of research. I wouldn't be able to say this is the best algorithm for all implementations because we don't have that.
Okay, thank you.
Yeah, sorry if it's like a non-satisfying question, but that gives you the opportunity, code up an algorithm, try different optimizers and see which one works better. You can try to study why is it that one works better than the other. People are doing that.
Yeah. Thank you. That is the nice part that you figure out what is the best environment for each one, because not all that problems are in the same environment. So I really appreciate your help.
All right. So I see that we have one question from YouTube. Is it always possible to encode an arbitrary computational problem as an optimization problem? Well, that is a great question. That is a really interesting question. So it can be quite hard. In some cases, if you have any arbitrary computational problem and you want to try to encode it into an optimization task, that in general can be very hard, especially if you want to encode it in a quantum computer, because even classically, right, you can think about classical algorithms for optimization tasks, classical computational problems, and trying to encode them into classical optimization tasks. That is not always easy. A lot of times what you do is that you reduce them to known problems, and then you know that that known problem can be translated into an optimization problem, right? And this is sort of how you build computational classes, right? You know that this sort of computational problems are equivalent, and if they are equivalent to one problem that I know I can encode into an optimization problem, then I know that I can encode this whole family. Quantum, it's even more complicated, right? Because a lot of times you need to define a problem with a cost function that you can efficiently estimate. And that's where the hard part comes in. And that's why defining and creating variational quantum algorithms is counterintuitive, because this is a task-oriented programming, right? As you said, we have to come up with the actual algorithm. What's the cost function? What's the ansatz to be able to solve this problem? And a lot of work has been developed in the last 3 years to map problems to optimization tasks. Like people have tried to work like, how do we try to map the problem of how a system evolves under an environment to an optimization task? Or how can we solve partial differential equations on a quantum computer? How do we encode this into an optimization task? That's precisely one of the large areas of research, which is trying to come up with a smart way to have a cost function that satisfies all of those properties to be able to build this. I don't know if there is a general way to encode an arbitrary computational problem. I would be tempted to say that there probably isn't. I don't have a proof for this. We can probably come up with a very complicated example that might be very hard to solve variationally or as an optimization problem. But for realistic and interesting tasks, that's sort of like the researcher's job. And this is where having a lot of knowledge about quantum information and quantum mechanics and linear algebra becomes really useful, because you're going to exploit those tricks in linear algebra and quantum mechanics and quantum information theory to create those cost functions. I don't have a way to get easy feedback from Facebook, from YouTube, without getting a bit of delay. So I hope that was a satisfactory question. A lot of times people ask me a question and I give more questions, and I'm just saying like, yeah, this is current area of research, which, I guess makes the field way more exciting. Right. So we have another question from YouTube. Is it always efficient to encode a computational problem as finding a Hamiltonian ground state? What's the motivation behind this mapping? So the motivation is that that's what people did the first time. That's the first variational quantum algorithm, was finding the ground state of a Hamiltonian. And a lot of times, even if you create algorithms that you're not explicitly thinking about finding the ground state of a Hamiltonian, there is a way to show that most variational quantum algorithms can effectively be thought as you have some effective Hamiltonian and you're trying to find the ground state, right? So that Hamiltonian doesn't have to be, a physical Hamiltonian. It's just a Hermitian operator, and the ground state corresponds to the solution of the problem. And the motivation is what we saw here, that whenever you're working with a cost function that is defined as the ground state of a Hamiltonian, a lot of times it's faithful, a lot of times it's operationally meaningful, a lot of times it's easy to compute. There are, of course, variational quantum algorithms that don't have a cost function of this form. I will give an example in just a little bit, but a lot of times it's not trivial to say, oh, in this case, my cost function is always finding the ground state of a Hamiltonian. That's not true. Many cases it is, and most of the ones that we're going to see, this is true. So, all right, if there are no further questions, let's go to trying to think about.
Can I say something before you start to continue again? So, in this sense, for example, how this process kind of avoid. I mean, for example, let me just try to establish the problem first.
Yeah.
In the case that the minimum that you mentioned on the graph there of the cost function, what if it's a saddle point? Could this procedure try to avoid those kind of situations? Do they do it at all, or are they just having the same problem as normal plastic?
So if you define your cost function appropriately, your solution should not be a saddle point. Because if your solution is a saddle point, then you have an ill-defined cost function. For instance, if you have a Hamiltonian and your solution to the problem is the ground state, then it's not a saddle point. It's actually the extrema. And it can be proved. And by the way, I forgot to mention, this equation right here, this is called the Variational Principle. And this is at the basis of guaranteeing that your ground state is going to be minimized at the solution. And a lot of times you have some quantum information principle, like the Variational Principle, that is going to guarantee that your solution actually corresponds to the global minima and not a local minima or a saddle point. That's the whole point, trying to define your problem such that, and that was precisely point number one, my cost function needs to be faithful.
I see.
You could potentially find cost functions where, this is not true, but that means that it's just a bad cost function. And you probably should redefine it and probably find another way of getting your cost function such that So that your solution corresponds to a minima.
Oh yeah, I know, but I mean, prior to start just using your cost function, you don't know if it's going to have saddle points or no. So
Oh, no, of course, you don't know that. It can have a lot of local minima. And in fact, variational quantum algorithms, there are non-convex optimization problems, just like a lot of classical optimization problems. What that means is that optimizing variational algorithms is hard because you don't have guarantees. It's not a convex landscape that you can guarantee that you're going to get to the minima after this many steps. Usually, variational quantum algorithms suffer from all the problems that classical algorithms for non-convex optimizations have, like local minima where you can get stuck. Your optimizer got stuck in a local minima. You didn't find the solution, right? Maybe you have like saddle points that can take you in the wrong direction. And on top of all of that, quantum machine learning also has the additional problem of noise, finite measurement. So in addition to the usual problems of non-convex optimization that you have in classical methods, variational algorithms have some extra problems. And we're going to discuss some of those at the end, like some quantum phenomena that makes optimizing quantum landscapes harder than optimizing classical landscapes if you are not careful.
okay, great, thank you.
All right.
Yeah, sorry. Just to add one recommendation that when we fall in a local minima is to repeat the search, increasing the stepping on every iteration in order to get out of the minima. But that's just a recommendation I heard once.
Yeah.
So maybe that can work a little bit.
That's absolutely, like, optimizing any classical or quantum cost function is an art. You pick up like ideas and things that that work, and you implement those. That's great advice. A lot of times whenever you're working with optimization algorithms, you don't want to have like a fixed step size, right? You do like an adaptive step size that can help you. You can also introduce noise so that if you stuck in a local minima, noise can kick you out of it, right? So there's a lot of things that you can do and a lot of tricks that you can do. If we get into the nitty-gritty details about optimization methods, that's going to be like a whole different course. But but that's a great advice, Diego. Thank you very much.
Okay.
All right. So now we're going to be talking about perhaps the most famous variational quantum algorithm, which is called VQE. This is the variational quantum eigensolver. As usual, I'm going to keep references here. I think this is the color that I'm using for references. If not, that's okay. This is Caruso et al. Nature Communications. This is 5.1, pages 1-7. 2014. It's quite old paper, but the idea is as important today as it was at that point. I will also give you the archive link. I don't know if you knew this. Maybe a lot of you already did, but if you look at an archive number, this right here is going to be the year in which the paper was uploaded to archive. So this paper was published in 2014, but it's been in the archive since 2013. So, it's a paper that has been out there already for what, 8 years? Yeah, it's been a while. And still, super powerful idea with a lot of implementations and a lot of power through it. So let's think about this. And we're going to think about the variational quantum eigensolver in the context of quantum chemistry, because this is the main idea for which this paper was developed in. So if we go back here, you're going to see that we are standing in the implementations of variational quantum algorithms right here. We've been talking about founding ground states. What is the ground state? How is the ground state important? Well, in this case, it's going to be quantum chemistry. So what is quantum chemistry? Why do we care about finding the ground state of some molecule? So quantum chemistry here, let's do again, as we usually do. This is the goal. This is the task. Because we have to start with a goal, we need to find the ground states of a given molecule, right? Why do we care about the ground state of a given molecule? Why would this ever be important? Well, a lot of times whenever you're trying to develop a new drug, for instance, what you're going to be doing is trying to simulate it and try to understand its properties even before you go ahead and synthesize it. Because synthesizing a new drug is usually extremely expensive. That requires a lot of work, a lot of fine-tuning, a lot of framework that you need to build to be able to synthesize that drug. So a lot of times it's very useful to know what are the things that you need to do prior, right? And maybe you don't just want to build a bunch of random molecules and then see how they interact with, like a virus or whatnot. You want to have some idea of what are the properties of that molecule. So a lot of times what you have is a Hamiltonian that is defined by what are the constituents of that molecule. And then what you want to do is you want to try to find what's the stable state of that molecule, which usually means finding the ground state. So trying to study the ground state of molecules and trying to understand certain properties of that ground state, like, if it's a protein, how is that protein going to fold? How is it going to interact with some receptor in a virus or a drug or in the body or whatnot? That's extremely useful and has a lot of applications for industry, for pharmacy, for new drug development, right? So a lot of times we can encode those sort of like big questions, this big pharmaceutical questions, into I want to find the ground state of a molecule. So this is essentially what we always want to do. And classically, this is very hard. This is precisely the example that we gave for penicillin. Finding the ground state of the penicillin molecule, that's a state that lives in a space of 2 to, I believe it was like 242. And we need a number of bits that is like 10 to the 71, order of the atoms of the number of the universe. This is not tractable for classical computers, right? So classical methods, usually what they do whenever they want to study methods is they use approximations. They try to simplify how the problem is defined to try to find an approximation of the ground state. And maybe that approximation of the ground state is good enough to answer the questions that we want to ask about this new molecule. But a lot of times it all boils down to our good old Schrodinger's equation, right? This is what we're trying to solve. What is the solution to this problem right here? What is the stable state of that molecule? And we're usually going to assume that H is independent of T. So this problem can always be thought about, yeah, I'm going to move the G here. So let's just redraw this. A lot of times this is going to be, I want to find a state psi, which is the ground state of this Hamiltonian. This is the task that I'm trying to solve, right? I'm trying to find the ground state. And this right here is what we call the molecular energy. So let's go to our question number one. What was our question number one? How do we encode this into an optimization problem? Well, it's very easy, right? We just find the ground state of this Hamiltonian. If we want to do this in a quantum computer, we're going to have a lot of problems, because what is this Hamiltonian usually going to be? So we need to think about, let's take a couple of steps backwards and let's go to basic hardcore quantum mechanics. What is a molecule? A molecule is, at the end of the day, a collection of nuclei and electrons, right? We're going to have a bunch of atoms, a bunch of electrons. They're going to be floating around, and I want to know how they interact. What we usually do is we have a structure of the molecule. We know what the constituents are. We know where sort of each one of them is bonded with whom. So we sort of know their positions. And what we're going to define is, this is going to be the R vector for the nuclei R, for the nuclear A. And this is usually going to be giving me some position, right? This is XA, YA, ZA. And I can do the same here. I know where this one is going to be around, or I can parameterize its position like XB, YB, ZB. And the same for the electrons. I can have like RJ is going to be XJ, YJ, CJ. Same for I. XI, ZI, YI, ZI. And then, of course, electrons and nuclei, how are they going to interact? They're going to interact essentially through a Coulomb interaction, right? So I'm going to be needing to parameterize what are the distances. So I can define a vector A, B, a vector A, I, vector I, J, B, J, And also, everything is interacting with everything. So I'm going to need RBI and RAI. Why are those important? Because how do I build a Hamiltonian of a quantum system? Well, I know that this Hamiltonian is going to be composed of NE electrons, each one with their positions Ri, and N nuclei. You know, I'm going to index those with I, J, K. I'm going to index those with A, B, C. And as we said, their positions are relevant, but also the relative distance, where I can define 1, 2 as, you know, x1 minus x2, y1 minus y2, z1 minus z2. And I'm also going to define here the Laplacian operator, which you all already know. And you're going to see in a second why I'm doing all of this and why we need to be careful just saying, oh, yeah, I'm just going to find the ground state of this Hamiltonian. Because we need to start with physics a lot of times. And the physics here is electrons and nuclei. So what is the Hamiltonian going to be? The Hamiltonian is going to have two terms, which we denote as T plus V. T is going to be the kinetic energy of the particles. V is going to be the potential energy of particle pairs, how each pair of constituents, particle pairs, are interacting. And usually you can split this in, you know, kinetic energy of the electrons plus kinetic energy of the nuclei plus the potential energy of electron-electron plus potential energy of electron-nuclei plus potential energy of nuclei, right? And, you know, we can even be more explicit and say, right, so we can write this as A going from 1, the number of nuclei. So let's just write this N, and I'm going to write this in a notation that people will be able to understand from their quantum mechanics course. So this is going to be the kinetic energy of all of the nuclei. We're going to have a similar term for the kinetic energy of all of the electrons. So I have 2me Laplacian squared, right? And then I'm going to have all of the Coulomb terms for the interaction electron-electron and nuclei-electron. So let me just write one of them. For instance, we can write the electron-nuclei one, which is going to be of this form. A goes from 1 to n nuclei. Summation of J goes from, let's use I. I goes from 1 to number of electrons, and this is going to be minus sign because they have opposite signs. So I'm going to get a minus here. Atomic number of my nuclei, charge of the electron squared, 4 pi permittivity of the vacuum divided by RAI, right? And I'm going to get here a term that is going to be of the nuclei, and plus a term that looks like this, that is going to be the Coulomb law for electron. So, of course, the question here is, this is a Hamiltonian that I have to find the ground state of. I have a superconducting qubit quantum computer, right? I can use Loic's quantum computer that is using Rydberg atoms. It has qubits. How do I find the ground state of this Hamiltonian, right? Like, this is clearly not expressed in a language that my quantum computer is going to be able to learn. So the first thing that we need to be careful is we need to be able to take this Hamiltonian and we need to be able to write it in a language that I can actually implement my cost function in a quantum computer. So here we need to do quite a significant number of steps, of historical steps that have been developed. But luckily, a lot of very smart people have worked on this problem for quite a while. And, you know, we can do a lot of approximations, right? We can do the Born-Oppenheimer approximation to try to treat the electrons and the nuclei separately, right? But of course, that's still not enough. We have here a Hamiltonian that is written in terms of position and momentum operators. Position and momentum. My quantum computer does not understand this. So something that I can do, let's call this the first part of my problem. Let's call this A, which is position and momentum. So what's the next thing that we can do? And I'm going to go extremely fast here because this is not an advanced quantum mechanics course. I just want to let you know the overall steps. of how you get to this problem, right? To this Hamiltonian that we can implement in a quantum computer. So the next thing that we can do, how do we implement this in a quantum computer? We use a method called the second quantization. Some of you might know about this, some of you might not. That is fine. We don't care too much about this. But essentially what this is that it maps H from X and P to a H that is written in terms of fermionic operators. And usually what we end up getting is a Hamiltonian that is going to be expressed from 1 to the number of orbitals. Let me just write this, and I'm going to say afterwards what all of this is. If you know what this is, great. If you don't worry too much about it. So these operators A that we have right here are called creation and annihilation operators. And essentially what they're doing is that they're keeping track of electron excitations. How are my electrons excited in the orbitals, right? Are they in the ground state? Are they in unexcited orbital states? So here, A dagger and A are creation and annihilation operators for electron excitations. Now we've taken a small step. Excitations. Oh, I wrote excitations very poorly. Let me just go back. And we've managed to map X as a function of XP to an X as a function of A dagger A. Is this something that my quantum computer can work with? Still no, because what am I doing here? I have a Hamiltonian that is expressed in fermionic operators, and the qubits in my quantum computer, they're definitely not fermions. So I need to do something else. I need to do another mapping where what I need to do is transform this into operators that my quantum computer can read. And what is the best thing for my quantum computer? Poly operators. So now we do a mapping to qubit and poly operators. There's different mappings that one can use. Let me just give you two examples, like Jordan-Wigner transformation or the Bravik-Kitaev transformation. I always forget. Yes, I think it's like this. If I didn't, I'm sorry. Which essentially what it does is that it takes creation and annihilation operators and is going to map them to something that looks like this. Sigma j minus 1 z tensor product sigma 1 z, where I encode the excitations of electrons into bit strings. And the more I encode the orbitals in what point in that bit string is the excitation in. Z tensor sigma 1 z. So now what I end up getting is a Hamiltonian that is essentially going to be of the form I alpha h I alpha. Let's use mu. This is a notation that we've been using. Mu sigma mu on qubit I plus summation of I j alpha beta I j sorry, this should be mu sigma mu in qubit I tensor product sigma mu in qubit j plus higher order polystrings. So finally, after all of this, we have a Hamiltonian that is expressed in terms of poly operators. And can we compute the expectation value of those poly operators in a quantum computer? Yes, we can. What do? We just measure in the computational basis and do a change of basis if that's not z, right? If this term right here is an x, we know how to compute this expectation value. So what we've done here is that we've mapped an h in x and p to an x to an h in a dagger a to finally an H that is expressed in terms of poly operators, right? And this is what we want. So you can see that this is to answer to the question, like, can we encode any arbitrary computational problem as an optimization task that we can solve in a quantum computer? It usually takes quite some work to get to one point to the other. And this is one specific example. You know, you've all heard about quantum computers for finding ground states of molecules. Well, this is all that you have to do to be able to implement that Hamiltonian in a quantum computer, right? There's quite a bit of work that goes here. It's not to say it's impossible or very hard. It's just to say that you need to be careful about what are the steps that you're taking. And here, just for to clarify, here we have second quantization. And here we have, for instance, the Jordan-Wigner mapping. And the question is, how do we compute my cost function? C of theta is nothing more than the expectation value of my parameterized state, this Hamiltonian. And we can do this classically and with post-processing. I keep using alpha, I should be using mu. All that I need to do is compute the expectation value of the mu operator on qubit I. And I need to compute all of those terms that I have in the summation, ij mu nu. Expectation value sigma mu I, sigma mu j. I'm gonna not use this notation anymore to save some time, and plus all the different terms. So in my quantum computer, I just prepare my quantum state, I compute all of those expectation values. Then I compute all of those expectation values and all of them that are here, and then I just put them together to form this cost function that we have right here. So now we have something that we can do in a quantum computer, right? Took us a while to get there, but you know, we can actually do it. So the next question is, how do we build? Let's just go back. Let's see the steps. So one, define a cost function. Because it's the ground state of a molecule, we know that it's faithful, it's operational and meaningful. It definitely cannot be estimated in a classical computer because we don't have enough computational resources. Is it easy to estimate on a quantum computer? Well, you know, it depends how many terms we have in that summation. We might have to drop some terms if you want to keep a polynomial number of terms and whatnot, right? So up to this point, so far, so good. Then we need to define an ansatz for U of theta. This is the first ansatz for U of theta that you're going to be seeing. Don't think that this is general. I'm just going to teach you very briefly about an ansatz that is used for quantum chemistry and exclusively for quantum chemistry. So this specific structure that I'm going to give you for U of theta is by no means general. It only works for quantum chemistry. It only works in this case, but because quantum chemistry is such a big deal, I definitely want to present it. So step number 2, ansatz. So how do we choose the parametrized unitary U of theta? And how do we actually even choose the initial state? So what is the initial state psi 0 that I want to be able to send into my quantum circuit? So in quantum chemistry, what people do is that the initial state, they're going to be using the Hartree-Fock state. And I think we touched a little bit based on this yesterday. I don't remember if it was during the lectures or during the exercises. And this Hartree-Fock state is just essentially obtained as the solution to the mean field approximation, of the problem. What is the mean field approximation of the problem, you might ask? If you don't know, it's okay. All that you do is you consider one electron, and I take all the other electrons and all the other fields, all the other nuclei, and I just consider them all as fixed. And I'm going to say I have one electron introducing with one very big fixed potential determined by everything else around it. So I have transformed this problem of multi-electron and multi-nuclei into just one single electron problem. And I do this for all of the electrons. I solve them, and then I repeat this process. I take that solution that I found for fixing everything, because how do I fix my initial electron, right? I fix electron 1 and I solve electron 2. But then when I fix electron, when I solve electron 1 and I fix electron 2, this is a new state that was determined by the previous state of electron 1, right? And I do back and forth until I converge to a solution. So here, what we get is essentially an input state that is going to be a product state. It's very easy to prepare, right? It's just I do some local rotation in each one of the qubits. So psi 0 is just essentially going to be obtained as initializing all of the qubits. and then doing some local unitary in each one of them. And I'm going to get here my Hartree Fock state, right? And this is what I get here. And then I need to implement the ansatz, right? This U of theta. So what is the ansatz that people use for quantum chemistry? I'm just going to name drop here something that I'm going to write it here in red in case you want to read more about it. It's called the unitary coupled cluster ansatz. So if you want to know more about it, you can go to Anand in archive 2019. Let me move this a little bit because I'm not going to have a state enough space. 15176. What this ansatz essentially does is that U of theta, and I see that there's a question from YouTube. I'm going to go to that in a second. It's essentially going to be of the form T minus T dagger, where what is T? Well, T are just operators that are defined as one body and two body excitations. So there's a quantum chemistry has been around for quite a while. They've developed those methods. And for instance, T1 is usually a summation of the form theta A B. Why is this not working? There it is. A dagger A dagger B. Then we have T2 are just going to be two body excitations, theta I J A B. A dagger A dagger B, A J A I. So essentially, let's think about what this is doing. We're starting with the mean field solution where the electrons are not interacting, right? They're just independent one from the other. And then what we're doing is we're implementing an operator that contains excitations. So we're taking the solution of the problem with no interactions. Each electron, remember, was independent from the rest. And we're going to excite that state. We're going to create excitations in one body and two body. And a lot of times this is enough. You could think about 3 body, 4 body, 5 body interactions and so forth. But it's been shown that a lot of times just one body and two body interactions are enough to get a good approximation of the ground state, right? And of course here, this is a unitary that is expressed in terms of creation and annihilation operators. We still have to map this to qubits, right? And now this is a good transition to the question. There's a question from YouTube that says, mapping from fermionic operators to qubit operators can result in non-local multi-qubit interactions. Of course it does. We saw it here. Will it be problematic to implement in NISQ devices? That is a great question. What is the locality of the operators that we get after we transform from fermionic to spin operators? Well, first of all, it depends on the transformation. Jordan-Wigner transformation, which is the one that I'm showing here, usually leads to larger polystrings, where I have a lot of polystrings that are concatenated. Bragg-VQE, on the other hand, only leads to shorter polystrings, usually of the order of log n, and that's why Bragg-VQE is usually recommended for quantum computing. Whenever we talk about estimating the expectation value of polystrings, we're going to actually see probably at the start of next course. I wanted to do this at the end of this course. I don't think I'm going to have time. That's not so much of a problem. The problem can arise when I have to implement those operators in the ansatz. Because remember, I have to have an ansatz that is expressed as the exponentiation of creation and annihilation operators. Whenever I transform those into spin operators, I'm going to have very large polystrings, right? And I'm going to have to implement maybe something that is of the form E of the I theta. Let's put this over 2 just for convenience. And maybe I have something that looks like an operator Y on qubit 0. Then I have like Z on qubit 1, Z on qubit 2, Z on qubit 3, right? And I have to implement the exponentiation of this very non-local polystring. Is this going to be a problem for NISQ? Absolutely. Why? How do I actually implement this, right? Again, we said we need to write our ansatz in a language that my quantum computer can do this. And we've already said that we're going to assume that we only have single qubit rotations and CNOTs. I don't know how to express this in terms of CNOTs. Again, if you check this paper on the archive of the link that I gave you here, they tell you how to do this. For instance, here, this is an operator acting on 4 qubits, right? 1, 2, 3, 4. We can actually implement this with a rotation around x pi over 2, just like this. And then we're going to get, and this is something that appears a lot of quantum chemistry, CNOT ladders, which sort of look like this. I might be doing a very terrible job at drawing CNOTs, but I'm going to try to do my best. And here, I can do a rotation about z of this angle theta that I previously have here. And then I have to do the reverse CNOT ladder. So I have something that looks like this. Then I have to do the CNOT from, let's see if I can get it. There you go. That's not that bad. It's almost a straight line. And then I need to do here an Rx of pi over 2. You can see that this Rx right here, what is it doing? It's literally changing the Z basis to the Y basis. If I had here something that looks like I theta over 2 x naught Z1, Z2, Z3, what do I have to do to change from the Z basis to the X basis? I have to do a Hadamard. So the circuit for this unitary right here would literally be something that, oh, what did I do? And I might be going a couple of minutes over. I hope that's okay with everyone. I'm going to try to wrap this up really soon and answer the question. This is a question that is taking a lot of time to answer, but it was a great question, so I want to give it the time that it deserves. This is the circuit to actually implement this unitary that we have right here, right? And what is the depth of this circuit? Well, it has a depth, so we can now start to think about big O notation. It has a depth of the order of length of the polystring. What is a polystring? It's just a sequence of polys, like we have right here. So if I have n qubits and I have a polystring that is acting on n qubits, just to implement one single gate of this form, and there's many of them, I'm going to require a circuit with depth n with a lot of CNOTs in the ladder. So this is extremely prone to error, and this sort of mapping to quantum chemistry is actually not the best because Jordan Digner actually, as you said, leads to very long polystrings, and implementing the UCC ansatz leads to very deep circuits that have a lot of problems to them. So yeah, thanks to the person in YouTube, that is a great observation. And that makes it such that, you know, the UCC ansatz is great. It's physically motivated. It's exciting the ground state of the mean field problem. So you take the solution without interactions and you start exciting it to try to get the solution of the interacting problem. But it has the problem that's really hard to implement, and it's going to lead to very deep circuits. So here we can see, and just very quickly, we have here a Y or an X. Why do we have a Y of an X? Here we had like sigma minus and sigma plus. And by the way, no one asked me what sigma minus and sigma plus is. So I hope you assume that you know what this is. Sigma plus and sigma minus are the so-called ladder spin operators. And you can write the spin, the sigma X and the sigma Y operators in terms of the ladder. I always forget this, so I might be getting wrong. Actually, let me just make sure that I write this correctly, because this is absolutely something that I get wrong every single time. So the plus is equal to sigma plus plus sigma minus divided by 2. Yes, that's it. And we can find a similar formula for sigma y in terms of sigma plus and sigma minus. So whenever we do T minus T dagger, just like we have to do here, we're going to get combinations that look like sigma minus plus or minus sigma plus. And that's how we're going to get bit strings that start with Y or with X. So this is essentially how we get to circuits that look like this. And these are very common circuits for quantum chemistry.
So sorry, just a question related to the diagram.
Yes.
Okay, the crosses in circles, what is the real meaning of that?
With one, what?
Okay, I mean the circles in the diagram.
Oh, the CNOT gate.
Yeah, exactly.
Perfect. Thank you for that question. I'm getting myself ahead. I told you that we had quantum circuits. Let me just go all the way back here because this is extremely important. Whenever we're talking about quantum circuits and universal gate sets, I told you, a lot of times we have this very important universal gate sets where we have rotations around the y-axis, phases, and CNOT. Well, CNOT is perhaps the most famous two-qubit gate, is the generalization of the NOT gate from using classical computing. And essentially what CNOT does is that based on the state of the first qubit is going to affect the second qubit. So the state has a control and a target. And the way that it works is that if my first qubit is in 0, it does nothing to the second qubit. If my first qubit, and okay, so this is the action on those two states, right? Because the first qubit is in 0. But if my second qubit is in 1, what it's going to do is it's going to bit flip the second qubit. So here, my control qubit is in 1, so it's going to bit flip the second qubit. So this is the action of the CNOT gates. And this is a gate that is extremely useful. And if you want, I can give you the matrix representation. 1, 2, 3, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0. It's extremely useful because it's part of a universal gate set. And a lot of times we're going to be using it as the solely two-qubit gate that we're going to be using in our circuits. So whenever I draw this, this circle, this is just a CNOT, where this dot here that is filled indicates that this is the control, and this right here is the target. So if this qubit is in 1, it's going to bit flip the other. If it's in 0, it's going to do nothing. So you can think about the CNOT as if my first qubit is in 0, I do nothing. But if my first qubit is in 1, I do a bit flip. What is the bit flip? It's just an X gate. And you can actually do this explicitly, and you're going to see that you're going to get this matrix via just, linear algebra. So, or you can also see it as the physical implementation, right? If this, then this. So if the first qubit is in 0, then I do nothing. If the first qubit is in 1, then I do a bit flip, which is the X gate, right? And the X gate is, of course, 0, 1, 1, 0, which maps me 0 to 1 and 1 to 0. So sorry, I got myself a little bit ahead. I know that some people here don't have a lot of experience with quantum gates. So the CNOT, it's in the theoretical exercises. I believe it's like theoretical exercise sheet number 2. But with this, I think this could be a good stopping point. Next time, we're going to see tomorrow, we're going to see other quantum operators, other variational quantum algorithms. Thus far, we're going to finish analyzing the variational quantum eigensolver, but we're also going to go to other parts of this board to try to understand how you can try to map problems into variational quantum algorithms. And hopefully all of this is, first of all, to show you that you need to follow this sequence of steps, not these ones, the ones that come after, to defining a variational quantum algorithm. Define the cost function, define the ansatz, try to find parameter initialization strategy and whatnot. They all follow the same structure. So at this point, I'm just giving you a brief, big overview of some of the most famous variational algorithms, because those are the ones that there's a lot of work and a lot of study being put on. And then we're also going to go and try to analyze more general problems that are not just finding the ground state of Hamiltonian, like the ground state of this molecule. And we're going to try to see if the cost function, as was asked, can still be interpreted as the ground state of some Hermitian operator that has nothing to do with the Hamiltonian of a physical system. We're also going to be able to answer the other question that I didn't touch today, which is we already know how to compute expectation values of single polys. You just measure that qubit, maybe change of basis. We're also going to see how to compute expectation value of multiple polys at the same time. Maybe you want to compute the expectation value of ZZ or ZX or YX, or maybe have more of them. So we're going to be working on that. That is also an exercise in the theoretical exercises. So hopefully you might get to that, or maybe you might get to that before we do. But with that, are there any other questions before we wrap this up? I know that I went a couple of minutes over, so sorry about that. All right. I don't hear anything, so I guess that with that, Felipe, if you want to just cut the YouTube transmission, remember everyone, we're going to do the screenshot right now. So please stay in line once Felipe tells us that the YouTube transmission has ended.